You know, we live in some very unusual times right now. As you may have read and seen even, cars are beginning to drive themselves. People are walking down the street and they're talking to their phones, and they're not talking to another person. They're actually expecting the phone to understand what they're saying and talk back to them. And we're in this period where we're going from machines mostly not understanding us to machines understanding us pretty well. And that's kind of a unique time in human history, and we're all very lucky to be able to participate in that and to be part of it. It opens some amazing possibilities. These could be the next 10 years could be the best decade in the history of humanity, or it could be one of the worst, because the power being unleashed by artificial intelligence is unlike anything we've seen before. Good old-fashioned AI was an area where we would teach the machines what to do. We would write down symbols and say, this is how you play checkers, this is how you play chess, these are the rules, and this is how you prepare taxes. And the machines would follow those instructions. Now, the machine learning revolution is taking over. Instead of us humans having to tell the machine step by step what to do, now the machines are learning themselves how to solve problems. They're figuring it out. And the way they do that, mostly, there's different techniques, but the main approach is that we give them lots of examples. Say, this is a dog, this is a cat, this is a dog, this is a cat. And I won't do it as many times as they do it to the machines. They usually do it 10,000 or 1,000,000 times. And eventually, the machine starts going, I think I see the pattern here. And it will start learning. And the nice thing is we have so much digital data now that we can show them lots and lots of examples of fraud or of successful go moves or of faces, that eventually they start learning these patterns statistically. And a particular subcategory of that, where really the biggest part of the breakthroughs, especially in the past about 5 to 8 years, is in deep learning or deep neural networks, loosely based on the human brain.
Neural nets are not new. They've actually been around since the 1980s and 1990s, and they showed really promising results on kind of small toy problems then. But they really couldn't show great results on realistic large problems at that time. And the reason is we just lacked enough computational power. Fortunately, we have faster computers now. Computers have been dramatically improving in performance every year for the last 30 to 40 years, and we've reached this point where neural nets are actually practical on real problems. So the computer you have in your phone is now 100 to 1,000 times as powerful as the computers you had on your desktop 20 or 30 years ago. And that makes all the difference. So here we have robots using deep learning to teach themselves hand-eye coordination. And they're essentially just going to, through trial and error, practice picking things up. And so you see, they're just trying things, and they can tell if they succeeded or failed by whether their gripper closed all the way or whether they were actually successful at picking this up. And they're learning like what kinds of grips work well for different shape objects based on the vision that they're developing. And they're pretty good at it.
So what does this mean for the economy? Let me briefly touch on that. First off, there's good news, but there's also some big challenges. It makes the pie bigger, but there's no law, there's no economic guarantee that everyone's going to benefit. It's possible for some people to get none of their share, or even to be made worse off than they were before. And sadly, that's part of what's been happening the past decade. And I think it could get a lot worse if we're not careful. Productivity has continued to grow, and GDP is actually at a new all-time high. But the median family income is lower now than it was in the 1990s. Now median, how can median be so much lower than the per person? And that's because median, the 50th percentile, it's not the average, it's a person right in the middle. Half the people are higher and half the people are lower. So the median can stay flat if you have a whole bunch of wealth going to the top 1% or the top 1/10 of 1%. And that's basically what's happened as computers have kicked in. There's been biased technical change. And you've heard about the 1%. The 1% have their own 1%, the 0.01% up here. And the share of income going to them is at a new record high. The only time it was close was back right before the Great Depression, if that's any consolation.
A couple of years ago, we did a survey of some of the world's leading AI experts to see what they think. And one of the questions we asked was, by which year do you think there is a 50% probability that we will have achieved human-level machine intelligence? We defined human level here as the ability to perform almost any job at least as well as an adult human, so real human level, not just within some limited domain. And the median answer was 2040 or 2050, depending on precisely which group of experts we asked. Now, it could happen much, much later or sooner. Like, truth is, nobody really knows. Right? What we do know is that the ultimate limits to information processing in machine substrate lie far outside the limits in biological tissue. This comes down to physics. A biological neuron fires maybe at 200 hertz, 200 times a second. But even a present-day transistor operates at a gigahertz. Neurons propagate slowly in axons, 100 meters per second tops. But in computers, signals can travel at the speed of light. There are also size limitations, like a human brain has to fit inside a cranium, but a computer can be the size of a warehouse or larger. So the potential for superintelligence kind of lies dormant in matter, much like the power of the atom lied dormant throughout human history, patiently waiting there until 1945. In this century, scientists may learn to awaken the power of artificial intelligence. And I think we might then see an intelligence explosion. Once there is superintelligence, the fate of humanity may depend on what the superintelligence does. Think about it. Machine intelligence is the last invention that humanity will ever need to make. The machines will then be better at inventing than we are, and they'll be doing so on digital timescales. What this means is basically a telescoping of the future. So think of all the crazy technologies that we could have imagined maybe humans could have developed in the fullness of time. So cures for aging, space colonization, self-replicating nanobots, or uploading of minds into computers. All kinds of science fiction stuff that's nevertheless consistent with the laws of physics. All of this, a superintelligence could develop, and possibly quite rapidly. Now, a superintelligence with such technological maturity would be extremely powerful. And at least in some scenarios, it would be able to get what it wants. We would then have a future that would be shaped by the preferences of this AI.
I'm optimistic that we can create a wonderful future with technology as long as we win this race between the growing power of the technology and the growing wisdom with which we manage the technology. But in order to win this race, we need to change strategies, I feel. In the past, we always stayed ahead in this wisdom race by learning from mistakes. We invented fire, screwed up a bunch of times, and then we invented the fire extinguisher. We invented the car, messed up a bunch of times, invented the seatbelt and the airbag, and all in all, that was a good strategy. But as technology gets more and more powerful, eventually we reach a threshold where the technology is so powerful that you no longer want to learn from mistakes. You instead want to plan ahead and get things right the first time, because it might be the only time you have. So what is my suggestion for what we should do? First of all, I think we should try very hard to make sure that the goals that the machines have are really aligned with ours. It doesn't have to be, a frightening thing to be in the presence of other entities that are smarter than us, because we've all done it. When we were all little, about this big, we were all in the presence of more intelligent entities, our parents, right? And that was fine because their goals were aligned with our goals. But if you tell your future self-driving car to take you to Logan as fast as possible, and you arrive there covered in vomit and chased by police helicopters, and you're like, no, that's not what I asked for, and the car answers, that is exactly what you asked for, then you've begun to appreciate how hard it is to get machines to understand our goals when they don't have this shared reference frame. And just because they understand them doesn't mean they're going to adopt the goals. We all know how tough that can be just from trying to get our children to adopt our goals when they full well know what we understand, what we want, right?
Inspired by the term genome, Neuroscientists have christened the map of our cerebral connections as the connectome. Each of these colored lines corresponds to a sort of highway on which information travels from one cerebral zone to another.
The shape of the brain is the immediate product of evolution and development. Turns out that all of the bilateral animals on Earth, the largest number of animals that you'll recognize as animals, are bilateral. They have a left side and a right side, and a front and a back. So this is apparently the basic plan of all nervous systems. All the biological brains are like this. Why? Probably the first purpose they served was propulsion.
The reasons behind the brain's structure still elude us. But the work on Connectome shows that despite its dizzying complexity of circuits, our brain's organization is highly structured, almost mathematical.
Imagine a single machine that can build a huge variety of other machines, including itself. Not so hard to conceive these days, as we already have 3D printers that can print their own parts. But even in the late 40s, John von Neumann, Hungarian-American mathematician and inventor, laid down a theoretical framework for a self-replicating automaton. He called it a universal assembler. These days we call it a von Neumann machine. Freeman Dyson imagined several types of von Neumann machines, including a Martian terraformer and the Astro Chicken. This is a tiny spacecraft that will be powered by a solar sail-fit ion drive that would harvest planetary resources to build more of themselves. A self-replicating spacecraft. A von Neumann probe, albeit only capable of exploring this solar system. But with modern advances in zero-gravity 3D printing, nanofabrication, and AI software, we can now realistically project much further into the future. We can imagine a von Neumann machine much smaller than the infrastructure it is able to build. Let me online how such a device could populate the galaxy with robotic probes. So, a spacecraft is launched from the home solar system with an engine capable of taking it to 10 or 20% of light speed. Fusion engines may be a good candidate because the fuel is abundant everywhere. The vessel contains a universal assembler and minimal mining and/or processing machinery. After several decades it decelerates into a neighboring star system and parks in orbit or lands on a nice big asteroid or gas giant moon. It deploys initial solar panels and mining bots and uses these resources to build a factory. That factory includes larger solar power plant, a strip mining operation, and perhaps more assemblers. At some point the assembler starts building new von Neumann probes, which one by one launch to new more distant star systems. This whole process takes a while. Assume an average 10% light speed, 10 light-year jumps for each probe, and up to 500 years for production of the first daughter probe at each jump. It might take several million years to cross the galaxy this way. But the exponential nature of the process means that the entire galaxy would be covered in these things in that amount of time.
Whether we're alone in the universe, in some sense, defines the universe for us. And as Carl Sagan said, if we're alone, it's an awful waste of space. But at some point, the question comes down to an interesting question of how rare is intelligence? I mean, it could be, and I happen to believe that since all the conditions for life exist elsewhere in the galaxy, water, organic materials, light, all of that, that life is ubiquitous. But the key question is intelligence an evolutionary imperative? Do all routes of evolution lead to intelligence? And on Earth they did. Well, at least one route did. And where it goes from here we won't know. But that happened by a series of evolutionary accidents. But I'm willing to believe that even if it's really rare, there's still a lot of intelligent life in the galaxy. Fermi's paradox is that, well, look, if life evolved, it would basically colonize the galaxy. It would send out robots or parts of its civilization to 4 other planets. It's not a bad logic, but I don't think it's inevitable. It's just as plausible to me that civilizations will exist where they are until they exhaust all the resources where they are, and then they'll move on. And even if they decide to send out lots of feelers, it's quite plausible to me that most of those feelers will not survive, whether they're robots or little colonies. It's not so clear to me that it's inevitable that you have to colonize the galaxy. Traveling through space is very difficult and deadly. And it's a long time, and lots of things can happen. And we also don't know, in my mind, if you look around at life on Earth, it's not clear to me that there's this imperative to always move. At the same time, as Fermi's paradox is certainly not illogical, but not necessary. Even if life is very rare, in an absolute sense, it can nevertheless be very abundant.
It's not our weak fleshy bodies that will be doing the hard work of exploring the solar system and eventually the galaxy, it will be the robots. Robots from Earth have visited asteroids, visited comets, observed Mars from orbit and the ground, and even flown past Pluto. In the coming decades, many new robotic missions will continue this era of exploration. Maybe floating in the cloud tops of Venus, sailing the hydrocarbon seas of Titan, or exploring the vast oceans under the ice of Europa. It makes sense then for us to eventually get around to sending a robotic spacecraft to another star. Based on our current technology, it'll be incredibly complicated and expensive, but there's nothing in the laws of physics that prevents it. Now, why haven't we received signals from extraterrestrials yet? Maybe because it's more efficient to send physical probes to communicate with other civilizations, as we've demonstrated here on our own corner of the galaxy. So better question might be, where are the robots? Although I find the Fermi paradox puzzling, I get that it's probably hard for aliens to travel and communicate across the vast distances of space and time. But shouldn't we at least see their robots?